Now that we've got a little bit more of a handle on working with quadratic functions and their graphs, we want to now solve quadratic equations and also bump it up to inequalities. So we're going to do a couple different things. We're going to first go through quadratic equations. Within that, we're going to go through a couple different ways to solve it. Afterwards, we're going to talk about a specific property or a specific thing called the discriminant and the properties it has. And then at the end, we'll go ahead and we'll solve some quadratic inequalities. So first and foremost, the quadratic equation is something we have been working with before. So in intermediate algebra, this is something you've seen, but pretty much it's some kind of equation that involves an x squared variable. So all of these values, a, b, and c, are just real numbers. We want to make sure just the value attached to a is not 0, otherwise that turns it back to a linear equation. So ultimately, we have 3 methods that we can use to solve these. The first one is definitely the easiest, which is factoring. So it's something we've had practice with before. It will work the best if it works. The problem is it's kind of a guess or check to see if that happens. So another method we have that's never going to fail is our quadratic formula. And that's definitely more tedious, but definitely not complicated. The third and final method is completing the square. So we did do a little bit of that when we were talking about creating the vertex, putting it in that standard form. We're not going to do this method for solving quadratic equations, but it is another method that exists, and it also never fails like the quadratic formula. So we're going to start with factoring. We're just going to work back with a simple example. So there's a property that we continually use. Whenever we're dealing with a quadratic equation, we typically want to get 0 on one side. So this way I have something times something equals 0. Because if we have that, then immediately you know one of the factors must equal 0. So from this, it's already factored. We can say either this first thing equals 0 or this second thing equals 0. Because the only way 2 numbers multiply to 0 is if one of them is 0. And then from here, we can just solve as we normally do. So we get x by itself by adding 2 over. And we get one solution of x equals 2. And then doing the same for the other, to get rid of that 3, we go ahead and subtract it to the other side. And we get a second solution of x equals negative 3. So when we're dealing with a quadratic, it's x squared. There's possibly 2 solutions. You might have one solution because it could be repeated, but typically there's going to be 2. Okay. So let's try some more examples. We want to solve each of these, and again, they're all quadratic, so hopefully there's 2 solutions, or again, 1 repeated. But the one thing you want to be really careful about is you want to always avoid dividing by a variable, because in doing so, you're going to end up losing solutions. So there's only one instance, which we will do an example of, where you don't move everything to one side. But typically, I always want to get 0 on one side of this equation. So for here, I want to move everything to one side. So I'm going to go ahead and subtract this 9x over. And that leaves us with x squared minus 9x equals 0. And now from here, I want to factor, and thankfully I only have 2 terms. Both of them have an x. So I'm going to go ahead and factor the x out. And what that leaves us with at the first piece is x, and from the second piece, a minus 9. Okay? Because if we go ahead and we distribute that back, you would see we get x squared minus 9x again. And then in the same thing as our prior example, I have something times something equals 0. That means this first thing equals 0, or this second thing equals 0. And thankfully for the first one, I don't have to do any work. I have x by itself. For the second one, we just need to add 9 to the other side, and we get a second solution of x equals 9. So again, this is where it's really, really, really easy to make a mistake, because a lot of times what will happen is, I've seen this on many exams, you want to solve for x, so people try to just divide both sides by x. and that leaves you with x equals 9. By doing so, you only end up with a single solution. So where does this other one come from? So when you divide by the variable, you end up losing a solution. So that's why we never want to do this. Instead, get everything to one side and then see if we can factor it. Okay. For this next one, we do have 3 different terms, but again, same thing. I want to get everything to one side, so I'm going to head and just move the 35 to the other. And that leaves us with x squared minus 12x plus 35 equals 0. And now from here, we've got to try to factor it. If you need some practice on factoring, there's tons of videos on YouTube that you can go to try to help you out. But remember, you're reversing the FOILing process. So the first terms should multiply to x squared. So the only way we can do that is with an x and an x. The last terms should multiply to 35. So 2 numbers that pop into my head are 7 and 5. Those multiply to 35. And since it's positive, they should both be the same sign, either plus plus or minus minus. But since we have a negative in the middle, it's going to make more sense to do minus 7 and minus 5. And to see if we've got the right factoring, we go ahead and check the outer terms, which is negative 5x. The inner term is negative 7x. And that indeed adds up to that middle term of negative 12x. So this is our correct factoring. And now that we have it factored, we go ahead and we just set each piece equal to 0. So either x minus 7 equals 0 or x minus 5 equals 0. And then for both of these, we're just going to add this constant to the other side. So I'm going to do both simultaneously. One solution we get is x equals 7. Another solution we get is x equals 5. So those are our 2 solutions. Okay. This next one is going to be this one example where I don't need to move everything to one side. So if you notice, we have an x squared term. We don't have any x's. So in this case, we're going to go ahead and we're going to get the x squared on its own. So we're going to go ahead and divide both sides by 2. So this leaves us with x squared equals 9/2. And now remember, to get rid of a square, we're going to take a square root of both sides. And that leaves us with x. And then we're going to have the square root of 9/2 over here. But remember, anytime you take a square root, you need to put a plus and a minus out front. And this gives us that 2 possible solutions. So just off to the side, I'll show you why. If I have the equation x squared equals 9, if I plug 3 in for x, 3 squared indeed equals 9. But if I plug negative 3 in for x, that also equals positive 9. So when I go to take a square root, you need plus or minus 3 to get both of those solutions, okay? So just anytime you take a square root, you need to put that plus or minus. And then from here, we just need to simplify. So we will go over radicals again in more depth in another unit, but we can go ahead and take the square root of the numerator and denominator individually. And the top does simplify to 3. The bottom, unfortunately, we can't do anything with. However, we don't like leaving radicals in the bottom, so we go ahead and rationalize by multiplying by root 2. So this gives us plus or minus 3 root 2. And then in the bottom, when you take root 2 and times it by itself, it cancels out and we get our 2 solutions. Now the next method is going to be our method that never does fail. The problem with it does take a while to simplify this expression, but really it's kind of just a plug and chug formula. So if we have a quadratic equation and the key being you have 0 on one side, then I can pick off the values of a, b, and c, and I just need to plug everything into this equation here. So maybe at some point you've already seen this, but if you don't remember it, you're definitely going to have it ingrained in your brain. One way you can kind of remember the solutions is you can sing it to the tune of Pop Goes the Weasel. So my voice is not great, so I apologize in advance. But it's negative b plus or minus the square root of b squared minus 4ac all over 2a. And that might help you remember just what the formula is. But again, you're going to get so much practice with it. You're going to use this a lot moving forward. So it's something that's going to stay stuck in your brain. So let's try quite a few examples. We want to go ahead and we want to solve this equation. The key being, though, I don't have everything on one side, so I need to move everything to one side. So what I'm going to do is I like keeping the squared term positive, so I'm going to move these other things over instead. And this leaves us with 4x squared plus 6x minus 9 equals 0. So again, I have to do this before I find my values of a, b, and c. Otherwise, I'm going to have some sign errors. So now I just pick off these constants in order and I keep the sign with them. So our value of a is 4, our value of b is positive 6, and our value of c is negative 9. And so immediately I can plug everything into our solutions. The values of x that solve this are negative b plus or minus the square root of b squared minus 4ac all over 2a. And this just leaves us with numbers, but this allows us to find complex solutions or potentially imaginary solutions too. So if you sat there and you've tried to factor and factor and factor and nothing is working, you probably have to use the quadratic formula. Or that being said, if you really hate factoring, you can do this approach to figure out the solutions. Because from here, all it is a matter of simplifying as much as we possibly can. So underneath the radical, 6 squared is 36. If you do 4 times 4 times negative 9, it's going to turn into a positive, and it'll be plus 144. And then divided by 8. So simplifying under our radical, 36 plus 144 would be 180. And then that's something I can keep simplifying. Okay. So you're trying to find a perfect square. You might recognize, oh, it's divisible by 4. You could actually take a lot out of this. So the biggest perfect square it's divisible by is 36. You can write 180 as 36 times 5. And then I'm running out of room, so we're going to go up here. Now I can take the square root of each of those individually. So this is negative 6 plus minus 6 root 5 over 8. Okay. And now I've got 6, 6, and 8. All of those are divisible by 2, so really you can take every single piece, divided by 2, divided by 2, divided by 2. And this gives us negative 3 plus or minus 3 root 5 all over 4. And that's as simplified as we can possibly make it. And these are the two solutions. The one solution is negative 3 plus 3 root 5 over 4. And the second solution is negative 3 minus 3 root 5 over 4. Okay. So again, this works on factoring. Absolutely can use it for that instead of factoring if you want. But the thing we're actually going to pay a lot of attention to is this expression that's under the radical. Because if you notice, that's going to tell us everything about the type of solutions that we possibly have. So when I took b squared minus 4ac, it gave us 180. Because this is the thing that goes under the square root, immediately I know now that my solutions are real. The other thing, square root of 80 doesn't simplify nicely, so this causes us to have irrational solutions, meaning that this radical is left over. If it happened to be that the thing underneath was negative, then I would be taking the square root of a negative number, and if you remember, we learned about complex numbers, that would turn into something that's complex. So this quantity b squared minus 4ac is what we call the discriminant. and its value tells us the type and number of solutions. So we have three possibilities as to what can happen. If the value of b squared minus 4ac is negative, then we're going to have two solutions. But because we're taking the square root of a negative number, they're going to be complex solutions. You're going to have the square root of something negative. It's going to involve I. Second possibility is this could be 0. So b squared minus 4ac ends up equaling 0. In this case, you're going to have a single solution. It's basically repeated because you would do negative b plus or minus 0 over 2a. Only one solution, the plus or minus part, disappears. And it's going to be a real solution, and it's going to be rational. So it will be an integer possibly, or an integer over an integer. And the final case is if b squared minus 4ac is positive, so I have the same exact last example, b squared minus 4ac was 180. You're going to have two solutions, and they're definitely going to be real numbers. Okay? But we do have some subcases under here. They're definitely real. They're going to be rational if b squared minus 4ac is a perfect square. So this way the square root would disappear. They're going to be irrational if b squared minus 4ac is not a perfect square. So that's exactly the last example. B squared minus 4ac was 180. So it was positive, meaning we had two solutions. They were real, but it's irrational because 180 is not a perfect square. Okay. So let's try quite a few examples. We're going to go ahead and we're going to evaluate the discriminant, and that's going to tell us the type and number of solutions. So we're going to do two examples. And again, for each of these, I could just find the solutions and classify them, but I don't need to go through the full amount of work. The other thing, if I just give you properties and tell you, oh, b squared minus 4ac is this amount, what kind of solutions do you have? You can't rely on using the formula to find them. So from here, I do have 0 on one side already, so I can go ahead and find my values of a, b, and c. Our value of a is 1. Our value of b is negative 5, and our value of c is 6. So plugging this into what's underneath the radical, b squared minus 4ac is negative 5 squared minus 4 times 1 times 6. Okay. So negative 5 squared gives us 25. 4 times 1 times 6 is 24. So b squared minus 4ac ends up equaling 1. Okay. So because of this, it's positive. This tells us there's two solutions. And further than that, they're real numbers. And because this is what's going underneath the square root, they're going to be rational. They're real numbers and rational numbers. Okay. And again, I could go ahead and I could actually find the solutions for this one. So our values of x would be negative b plus or minus the square root of b squared minus 4ac. We did that. So it's going to be 5 plus or minus the square root of 1 over 2a. So really you get 5 plus or minus 1 over 2, which leaves us with 5 plus 1 over 2 or 5 minus 1 over 2. So 5 plus 1 over 2 is 6. Divided by 2 would be 3. And then 5 minus 1 is 4. Divided by 2 is 2. So you see we got two real numbers and they are rational. We can even take it a step further and classify them as integers, but this is sufficient for us. Okay. For this next one, I unfortunately don't have 0 on one side, so I do have to do some work first. And again, You could just move the 3x squared over, but I like keeping the x squared positive, so I'm going to move the others over instead. So this is 3x squared minus 4x plus 5 equals 0. And now we can say our value of a is positive 3, our value of b is negative 4, and our value of c is positive 5. So plugging these in, b squared minus 4ac will be negative 4 squared minus 4 times 3 times 5. So this leaves us with 16, and then if you do 4 times 3, that's 12, times 5 again. This is going to be 16 minus 60, which leaves us with negative 44. Okay. So the value of b squared minus 4ac is negative. Immediately that tells us there are two complex solutions. Okay. And again, if you want to actually find them, you can. The actual solutions are negative b plus or minus the square root of b squared minus 4ac, which we figured out, all over 2a, which leaves us with 4 plus or minus root 44i over 6, which then can be simplified from there. Okay. So you can go about and you can simplify it if you want, but they are imaginary or further complex solutions. Okay. All right, so our very last thing that we need to do is we need to go through quadratic inequalities. These are a little bit nicer than our absolute value, and they're more comparable to when we get to rational inequalities and radical. But the number one thing you have to remember is that you never want to divide by a variable. The simplest thing you can possibly do is really solve the corresponding equation, and that's going to give us important numbers to do our interval testing. So the very first thing we need to do is move everything to one side. Then we want to solve the corresponding equation to find the important numbers. Then we're going to use those to divide the number line into intervals, and we're going to test each interval. So I'm going to show you with this first one kind of the more drawn out process, and then when we go to the second one, we can kind of do a little less work than we need to. But I'm also going to relate this to our quadratic function as well. So the very first thing I want to do is I want to move everything to one side. The easiest way to do that is to move the 15 over. So that gives us x squared minus 2x minus 15. And we want this to be greater than or equal to 0. So to find my important numbers, I'm going to go ahead and I'm going to set this equal to 0. And just as kind of a key tip, this should always factor because you have to do interval testing. So x and x give us x squared. To get to negative 15, we can do negative 5 and positive 3. And you can check the outer and inner give us what we want. So we end up with two important numbers, positive 5 and negative 3. Okay. Now that we have that, I want to go ahead and create a number line. And we're trying to test, is x squared minus 2x minus 15 greater than or equal to 0? And we're going to put these two important numbers in order, negative 5 and 3. And then it creates 3 separate intervals we need to test. For the endpoints, because we have the greater than or equal to, we can fill in these circles. If it was strictly greater, I would have to leave them open. And now I need to pick something from each interval to test. So from our first interval, let's go ahead and pick negative 4. If we plug that into the inequality, that would be negative 4 squared minus 2 times negative 4 minus 15 needs to be greater than or equal to 0. This is 16 plus 8 minus 15 is greater than or equal to 0. And then 16 plus 8 is 24 minus 15. This is definitely greater than or equal to 0. So this first interval is going to work for us. Okay. Moving on to interval 2, a number that falls in there is 0. That's always a nice number to plug in. That would be 0 squared minus 2 times 0 minus 15 is greater than or equal to 0. So that is negative 15 is greater than or equal to 0. And unfortunately, this one does not work. So interval 2 is no good. Moving on to interval 3, let's go ahead and pick 6. This would give us 6 squared minus 2 times 6 minus 15 is greater than or equal to 0. And that's 36 minus 12 minus 15 is greater than or equal to 0. And if you do 36 minus 12, that's 24. Minus 15 is greater than or equal to 0. This is definitely good as well. So everything in interval 3 is going to work. So our solution to this inequality is interval 1, which is negative infinity to negative 3, and we can equal that. And then our third interval also works, which is 5, which we can equal to infinity. And so these are the values that satisfy the inequality. Okay. Now again, I do just want to relate this to the graph so you can kind of understand why. I know we haven't talked a ton about x-intercepts or anything like that, but remember the x-intercepts are where the function equals 0. So that happens to be at 5 and negative 3. This is where our graph is equal to 0. And it's x squared, so it would be a parabola that opens upwards. You could definitely find more detail. But this would be the graph of x squared minus 2x minus 15. And what the inequality is really asking us is, where is this graph greater than 0? And that's going to be on these two branches right here. So it's exactly from negative infinity up to negative 3, and then from 5 onward to infinity. So the reason these numbers are important is it's because it's where our x-intercepts occur. So it's where we potentially can pass through the x-axis and make our function go from negative to positive. So this is why we always want to get 0 on one side of the equation. And this is going to be true when we deal with rational inequalities and radical inequalities. Okay. So let's try one more, and this one I'll do a little bit of a shortcut with. We don't necessarily have to solve the equation. We know we just need to factor it to find those important numbers. So here we go ahead and factor. We need an x and an x. To get to 24, we can do 8 and 3. And then since it's positive, that means they have to have the same sign. So we're going to pick negative because it's negative 11 in the middle. The outer term would give us negative 3x. The inner term, negative 8x. That indeed gives us this negative 11x in the middle. So this is factored as much as possible. And so our key important numbers would be setting this thing equal to 0. So that's going to happen at 8 and 3. Okay. So we go ahead and we create our number line and we put those in order, 3 and 8. And then again, this splits it into 3 intervals that we need to test. And we're trying to see, is x squared minus 11x plus 24 less than 0. Unfortunately for this one, because we have the strict inequality, we cannot fill in these circles. They have to stay open. All right. Now from here, let's pick something from interval 1. 0 happens to be less than 3, so that's always a nice number to use. This would be 0 squared minus 11 times 0 plus 24 is less than 0. This tells us 24 is less than 0. So unfortunately, interval 1 does not work. Moving on to interval 2, we can pick 4 inside that interval. So this would give us 4 squared minus 11 times 4 plus 24. We want this to be less than 0. So that's 16 minus 44 plus 24 is less than 0. And if you do 16 plus 24, that's 40. And then we're subtracting 44. We want this to be less than 0. And I don't need to finish this completely. I definitely know that's less than 0. So everything inside interval 2 is going to work for us. And then finally, from interval 3, let's pick 9. Again, you can pick whatever you want though. We're going to do 9 squared minus 11 times 9 plus 24. We want this to be less than 0. 9 squared is 81. 11 times 9 is 99 plus 24. If I do 81 plus 24, that is 105 minus 99 is less than 0. And unfortunately, this interval is not going to work because that would be 6 is less than 0. So only interval 2 is good. So our solution starts at 3 and goes to 8. And again, if you want to connect this to the graph, 3 and 8 correspond to where the function equals 0. So those are the x-intercepts. And then from here, it's positive x squared. So it is a parabola that opens upward. So I know its graph looks roughly like this. X squared minus 11x plus 24. We want where the function is less than 0. So that's where the function is negative. That happens in between 3 and 8. So again, exactly the same thing we got from doing our interval testing.